the instructions. It's not really a huge matters, but for now, your instructions is about 50 pages, I believe. 49 pages. What's that? Why so short? It's the longest one you got in this class. But nevertheless, I have provided all the help I can give you in the instruction. If you carefully read instructions, you should have a good understanding towards what you are implementing, what exactly the desired output I am expecting from you, especially go to appendix B. So which it is not clickable on this part. So simply you have the terminal output, you would have some ELF output, and then you have the virtual machine running result, everything here. So again, for this homework, I will no longer be able to verify your test cases. And all the TAs will no longer to perform that. Simply, you have your way to verify whether it's correct or not, basically through your virtual machine. Any question? If it's legitimate correct input, it will produce the correct output. And that correct output, which is the ELF file, will become an input for your virtual machine, and your virtual machine should be running perfectly for that legitimate input, okay? That is the way you can verify whether you are generating correct output or not. Any other question I may have? Anything? No? That's it? Good. And as you may see, you got a lot more quizzes to practice on, and each is worth about 25 questions, 32, 23 questions. And once we finish the lecture 14, you will get another 49 different questions to practice on. So, yes. Yep, go ahead. You will not get any extra points. So you will be capped at 14,000. Any other question I may have? That's it. And I think that's everything I can give you for now. And you could expect your final exam to have around 50 different questions in the final exam. Yes. What's that? Yeah. The finals you can literally find from here. How long is the final? You tell me. Yeah, it is 2 hours and 15 minutes. That is why we could have 50 different questions. But where is those 50 questions coming from? Directly coming from the practice quizzes. This basically is what I'm crafting towards the final exam. If you can perfectly practice whatever the practice question you have, you got perfect score, you understanding every material, understanding everything, go to the final exam, you know all the questions I'm being asked, then just simply answer that. You could presumably finish this final exam within 1 hour. Okay, yes, question?
Did you say 50 like potentially, or that's what you actually want to do?
That's actually what I'm want to do. So simply, I'm considering if you can finish. Simply, what we have here is all conceptual questions. The majority of the question will be conceptual questions. Simply ask you whether you understand this concept or not. That's it. Just multiple choice, true and false questions. That'll be it. There will be about 5 questions that is tackling your understanding towards your homework 3 and 4. That'll be it. nothing really fancy or hard right here. If you practice, you should get a decent score. Okay. I'm all tagging about your understanding towards the material. Okay. Anything else? And of course, you are going to have your cheat sheet. Yes. Lecture 9 and onwards. And we are going to have a couple questions from the previous the midterm. It is accumulative, but I'm sure about before the midterms, concept will only counting towards 20% of the entire grade. If you simply miss out whatever you have studied on in this 20%, you still got 80% in total. So again, final exam to be extensive is 2 hours in total. 2 hours, 15 minutes. I think it's legitimate to test whether you understand the entire lecture or not, entire course material. Yes, question, concerns, feedback, complaints? Anything? Yes, complaint? Yeah. Homework 3, I will release the homework 3 grade. We got 40 of 177. They are still working on that. Hopefully they can get everything being graded by the end of today. And simply I can release all the grade by tomorrow. So you got your feedback, you have everything. If you have any concerns, you can talk to me or talk with TA. Any other things I need to know? That's it. It's been a lot of work for me. So it's quizzes I developed them by tomorrow, last night till like 10, 11. So it is what it is. I have worked my hard time. All right, so let's coming back to what we have learned. Before that, Tuli, no questions at all? Really? Nothing? Okay. Then it means you understanding everything. Okay, go practice. So let's talk, coming back to this slide we left on Friday. So we have the PSW, and PSW have covered all kinds of things. Now we have 4 different interrupt flags. They are OV. What is OV? What up? Overflow, MP, memory protection, PI, privilege instruction, of course, IO. IO is IO. And what is mode? We have talked about mode. What is mode? User mode or administrator mode or supervisor mode, and how is being used combined with what flag? Come on. User mode is always combined with another interrupt flag, which is what? Privilege instructions, of course. That is what we have learned. Now, what do we have? All the basically all the flags and the mechanism being placed right here, and we need to describe the CPU interrupt cycles. In other words, what does the CPU do each step to handle the interrupts or traps when they occur? So what we have here on this slide is basically the pseudocode or the flow of this interrupt check phase that CPU would perform internally. And so the first thing is OV equal to 1. Of course, we need to check all the traps, OV equal to 1, MP equal to 1, or PI equal to 1. Simply, we have the new PC signed to the PC. These are all the same across the board. Why are we signing a new PC? Go to that, what? Interrupt handler, right? Interrupt handler subroutines, and mode is equal to 1. Why are we setting the mode equal to 1? Tricky? Why are we setting up in mode equal to 1? Mode is what? 1 is what? What's that? Admin mode? is supervisor mode. So to be particular, supervisor mode. So why are we setting up the supervisor mode? Because whatever like interrupt handler is, it is within the memory boundaries. So which user mode cannot execute. You have to invoke supervisor mode in order to execute that error interrupting handler. Then abandon, what exactly abandon notify you? Simply abandon means we are abort this program. That is why we have setting up the new error routines. Once we have the supervisor mode being set, we can go to the interrupt handler, whatever is going to be. Once we're coming back from the interrupt handler, we are going to abort this program. So that will be it. Then we come into the IO. IO is the very specific like interrupt process that we have IO equal to 1. It means we have to go to that IO interrupt, finish out that IO interrupt. And once we come in from the interrupt, we want to resume whatever the program is, because it's a hardware interrupt. We still want to resume our program. You don't want to open up file and abort your program. You want to continue your program as much as you can. So how we can continue that is basically saving all the states of the program running state in some registers. We have the OPC, which is recording whatever the programs is executing the next, your programs executing. Then A, so sometimes you are dealing with arithmetic. So you have to save in that arithmetic basically result or the temporary result in a register. It may be overwritten in the accumulators. Therefore, we want to save it. Yes. What's that? Why we're setting up the new PC? New PC is the first instructions of the error handler, interrupt handler. That is why we sign in the new PC. Okay, it's a fixed address and within the memory boundaries. If you go back to the previous slide, I think is about 20 or 30 slides. So you will find that slide to talking about the new PC. Then we have the new PC assigned to the PC again, basically go to the interrupt handler, doing whatever it is going to do, and the mode is setting to 1, specifically an administrator mode or supervisor mode. We want to be, particularly in this class, we want to call it supervisor mode. No other terms will be talked about right here. Then decoder 00 going to fetch cycle again. That's it. Then we're talking about a lot of things like transferring the control to supervisor or OS. So we have to clarify what the supervisor role is. So the supervisor, we have another name for the operating system or in its privilege mode. So exactly the same things. We have a supervisor, we have an administrator, we have all operating system, exactly the same thing in this lecturing context. You have to understand that. But once you go to the industry having a different terms to be defined in different contexts. Operating system is operating system. It doesn't necessarily mean it's having the supervisor mode or privilege administrator mode. So just be sure what we have here is in this context, supervisor mode, operating system, and administrative mode simply is the same thing, okay? Now, we have a supervisor mode can execute both user level and privileged instructions. That is, it has full access to the machine's capabilities. So now, the question is, why would we need to invoke supervisor intentionally alongside these error conditions? Have you ever thought about that? Yes. Not necessarily. So basically, what we have said, we want to invoke a supervisor mode intentionally. So why is that? Because sometimes a user program may need to do something that is not allowed to do on its own. For example, if you have your Mac OS, you install the Zoom, and Zoom is telling you, I want access to the webcam, I want access to the microphone itself doesn't have the privilege to execute that information. You have to give the administrator mode to it to enable it to modify your system privileges so that it can has so basically the access to your webcam or the microphone you have on your laptop. That is a privilege mode. Again, so for example, a user program might need to open up a file and read something from the disk and write it to an output devices, etc. Those operations, again, all typically involve hardware access and must be done via a privileged instructions or at least controlled procedures. So user program running in user mode cannot directly execute basically a device read instructions or manipulate the device registers. If it tried, simply the hardware will simply trigger the PI flag for something went wrong. I cannot allow you to do so. And so then the question is, how does the program get those essential tasks to get done? We have to have some kind of interrupt, and it should have some intention to interrupt for that. So it needs a mechanism to request the service from the supervisor. In other words, the user code must be able to call upon the OS for help in a safe and controlled manner. So the concept we use for this is system call. Instead of a user program executing a privileged operations outright, it will ask the OS to do it on its behalf. What we have here on the slides is simply sets up the stage list by saying sometimes here. Sometimes the user program requires services of supervisor like file IO, since they cannot do those directly. And though there must be a way to communicate with the supervisor. So this is the mechanism what we call the supervisor call, which is on next slide. So the mechanism for the program is to voluntarily invoke the OS is called supervisor call and SVC for short. So SVC is essentially the same thing as we generally call a system call. So it's an instruction or a set of instructions and designed to request a service from the operating system. So when a user program executes a SVC, it simply triggers a software interrupt. Basically, the program is deliberately causing an interrupt to switch the CPU into the supervisor mode because this is triggered by the program's instruction. We simply call it software interrupt rather than hardware interrupt, as opposite of some external hardware interrupt. And such as we will see in later of the slides, and we have discussed the one hardware interrupt, which is what? IO interrupt. IO interrupt is a hardware interrupt that's initiated by the system, not you. And of course, what we have talked about, the difference between this traps is that SVC is intentional. It's usually not an error. It's a normal way of a program transitioning into the OS code to say, let's open up the file, let's allocate some memories, and under the hood, the SVC instructions causing the CPU to relinquish the control to the OS in a very controlled manner. So what we have here on the two types of system calls, in a sense, will be this slide on here. The first type is explicit service request via special instructions, essentially the SVC instructions themselves. So those are defined to be legal in user mode. They would have opcode below some of our privileges range, such as we have defined 0 to 59. Those are the instructions the user mode can execute. That's totally legitimate. And they simply cause an interrupt to the OS, but the instruction is not considered as illegal. It's simply designed for that purpose. That's the first type. The second type is basically the privileged instructions we discussed earlier. That is the opcode with the opcode beyond 59, 60 to 120, let's say. A user program somehow attempts one of these, it simply triggers the PI trap. In a broad sense, it also handles the control to the OS, but as an error condition rather than a request. So effectively, the system has an intended system calls, that is SVC instructions, and unintended ones, that is privileged instructions, that both land you to the supervisor mode. But once we're talking about SVC, we are focusing on the proper mechanism of a program uses to get OS services, SVC, which is equal to a clean software interrupt. Let's say, hey, OS, I need some help. Can you do something for me? And then the OS will figure out which service is being requested by looking at some indexes or code associated with this SVC call. So, but once we're talking about indexes and associate, how it's going to figure out what exactly the service we are landing on or what exactly the program we are calling. So this is called SCVT. SCVT is basically telling us this system called vector table. You can consider as a single array, 1D array. So the SCVT is essentially lookup table in memory, each entry in the table corresponding to a specific system call, a specific service. So for example, entry 1 might be open up file service, entry 2 might be close up the file, and 3 might be write, 4 might be read, so and etc. So we could have a lot of more little mini services, and each containing an address of the code that implement that service. So when the SVC interrupt happens, the hardware or OS will use that index provided by that SVC to index into the SCVT, the table we are talking about. And CVT entry gives the memory address where the actual service routine begins. In other words, SCVT holds the starting addresses of the OS routines for each possible service call. So what we have here on this slide is basically a good words to explaining what exactly a service call is. And what do we have here? Service call are actually a tiny programs themselves, since performing something like file read can take several instructions. Therefore, each service has a routine typically written in assembly language, which is for efficiency and low-level controls. And CVT simply points to those routines. Think of what do we have here? If you want to think about a CVT, you can think it's a 1D array, or you can think it's a jump table. So SVC instructions with code X will simply triggers that jump to the address stored in SCVT. Basically, how you can access it, if you consider as 1D array, you simply has SCVT and square bracket X and square bracket to enclose that to access the information. So this design making the handling system more flexible. Basically, if you want to add a new system call, so you have something new in your system, operating system, simply adding a new entry in this SCVT and basically letting the programs know, okay, I have adding a new simple the system call, so you can interrupt me for this one, and that will be it. So that's the modularity we're talking about. So let's talk about how user program actually invoke this system calls in practice. Usually a program doesn't manually issue the exact trap instructions with a number. So instead, it simply calls a function in a runtime library. So library does the low-level SVC for it. So runtime libraries is a collection of pre-written and pre-compiled procedures that programs can use at runtime. Hence, name runtime library. Okay. Then, for example, you have get used to C. To be particular in this class, in this university, C is the first language you should be studying on. And the C program might have in some, for example, printf or F opening. That is not part of user code per se. You simply cannot write by yourself, like, I want to print something to the terminal, to the display. How you can do that? By simply invoking a function, that is the thing you can only do. You can say, oh, that's the thing I need to invoke. But is it necessary to be that implementation? But your system, your runtime system will figure out what exactly the devices you have right now. Is it device 1, device 2, device 3, and how you are going to write it, in what encoding, what is mechanism to write on that, what is the rendering mechanism for this display. So they are all doing the hard work for you. That is runtime environment, runtime libraries. And they are provided by C runtime libraries. Underneath that, they might be invoking the system calls, what exactly system call is. Open up the IO interrupt, and we have something to write on the display, figure out in what is rendering, what is the character, what is the encoding, is UTF-8 or UTF-16 or some kind of ISO encoding, etc. So in our context, the runtime library routine for say, just simply reading a file will contain the SVC instruction to trigger the OS service. When such a library routine is called, for example, it's with a special flag, SVC flag will be set to 1. This happens as a part of executing SVC instructions. Simply, we are going to set SVC instructions or SVC flag to causes the CPU to switch to the CPU or supervisor mode in the same way as interrupt do. We have IO interrupt, OV interrupt, MI or MP and PI, those are interrupt, simply that as that flag. So in fact, SVC is an interrupt just as initiated by the software intentionally. And there are a couple important properties I want you to remember on this slide. So first, they are all shared by the program. So the runtime libraries, they are all shared by the programs. That means the code for say, reading a file or printing to the screen is kept in one place in memory, and all user program can use that same code rather than each program having its own copy. If we are performing that copy for each program, basically you should have a larger memory slots. Currently, the majority of us only having about 16 gigabits of memories. If we are doing one copy for each programs you are running on your laptop, you should have about 64 gigabits of memories, which is infeasible. That is why we have a dedicated place to place all the system calls or runtime libraries that is available for all programs. Then next property is they are protected. No program is allowed to modify the code of the runtime library unless it is initiated by the OS or some other manufacturers, for example, C compilers. And since they are residual in the memory areas, the user program normally or typically cannot write to, perhaps mark as supervisor or read-only segments. The integrity of those routines is ensured. So this is a very critical step because it is if, let's consider, a malicious program could alter the runtime library routine that performs SVC, it could trigger a trick the OS or compromise the systems. So the runtime libraries should be acting as a safe interface. The user program calls a function which is allowed to do so, and library functions execute SVC, which triggers the OS because the library code is trusted and unaltered. So we maintain the security and stability. Then what really does a SVC instruction look like? You should have having this question in your mind. The format is given by this thing, the SVC index. The index here is basically a number identifying which system call we want. For instance, if index is 4, it means read system calls or read system call. SVC is equal to 1, and it means open up the file or something else. So it's basically coming from SCVT. We haven't talked about SCVT particularly. We will touch on this topic in later of the lecture, so you don't have worries. You just think is a lookup table. That'll be it for now. Okay, in machine terms, SVC instructions has opcode, which tells the CPU this is a supervisor call instructions, and operand that is index. And so inside of the instruction registers, you'd have something like ir.op equal to SVC, and ir.address is equal to index. This slide even giving a little bit of example right here, which is how you invoke the SVC calls, is basically SVC equal to 4. That'll be it. Okay, so whenever a user program calls a library functions, it wants to do something read or something open a file, it basically internally executing something like SVC4. So this causes the software interrupt, and the CPU upon seeing this opcode for SVC will treating as interrupt trigger. And this basically setting up SVC flag to be 1, for instance. Now, let's walk through what happens when SVC instructions execute in real time. So we will use the example for this one, the SVC index calls. And the moment the CPU recognizes SVC instructions, it begins a sequence, much like handling the IO interrupt. Since SVC is essentially a software interrupt, then sequence would be this one, which is displaying on the slide, saving the current program state, which CPU takes the current CPU, current PC, which points to the next instruction after the SVC, and saves it into an old PC register. And also we have some kind of saving some register. For example, if we are dealing with accumulator, we could have old A register to save that accumulator content. For this one, we also need to save ir.address to be a temporary register that is called B. Simply, we wanted this information because once we're coming back from the state, we want to resume whatever is being paused right there. Then RTL addresses, we will talk about RTL addresses to be specifically, but this time you think it is as a new PC. Simply go to the error interrupt handler routine. But RTL addresses will be addressed in later of the lecture, so don't worry about it. Then we have the decoder is equal to 0.5. We have learned this one a lot of way. So what is 0.5? What's that? Yeah, interrupt cycle. That'll be it. 0.5 interrupt cycles. Then we're coming back to the von Neumann virtual machine. We are basically expanding it. So we have the OPC is saving the current PC, and we simply consider the RTL addresses is the interrupt handler address. We simply assign to the new PC, to the PC to be executed. What is the next instruction? That is an interrupt handler. Then we have address is being recorded as B. Of course, we also can have A to record the accumulator. So that is the idea we have. This is the expansion of our von Neumann machine. Now, we have to understand. Yes, question. OPC will be replaced. So this is an issue that we will discuss in later of the lecture. That is becoming an issue. So for now, the OPC will be replaced if we are having multiple interrupt and happens. Okay. Now we have to solidify what is SVC concept with a concrete example that is present here. So imagine you have your user program that is written in this way. You have something that are calling a runtime library that say read. So which internally executing SVC4, let's assume 4 is the code for read service. So now it's playing out in this like step-by-step manners. It's simply the user program calls the library read routine in the user mode. And when the program hits SVC4 instructions and SVC software interrupt is triggered, we already described as the hardware action. The CPU will set simply saving all the state. So to the OPC or A to the OA and ir.address to B register, that's saving all the state of your user program that is being saved right here. Now, the interrupt cycle. So since the SVC flag is being set as 1, and we have some interrupt cycles, and simply having SVC flag is set to be 1. And at this position, and we go to the basically finding what exactly the interrupt we are dealing with. So SVC flag is equal to 1, and then simply we have SCVT lookup table to find the mini program we are doing. Is it read? Is it open? Is it something else? For the interrupt handler, go to that table to find a new address, assign that new address to PC. And then based on the PC instructions, we simply replace whatever the content in here to be that particular mini program's content. So we execute whatever the information right here, then we are restoring back to the runtime result that is basically restoring SVC flag to be 0 and continue. Then we have lastly, the old PC is being restored, then you can normally resume your user program. So in other words, to be precisely describing this slide, what is the flow? It will be your user program starting on the left, have SCVC4 system instructions, go to a runtime library to figure out what exactly the read is. Then we find SVC4 is being set as 1. Then we simply go to interrupt cycle to talk about, okay, that is the mini program you are dealing with. Go through that information and return whatever the information is. Go to that runtime library, finish its job, and then return back to or resume your user program by using the old PC. Okay. So that is being short. So now we update our master interrupt cycles logic to include the SVC flag along with the others. Simply, you can see a new addition to our interrupt cycles. SVC1 is being added, and simply we are saving to be more simple way. We're only saving the PC to OPC. That's it. And IR.address is not being saved simply for it's just for simplicity here. You don't have to memorize everything, but simply we have this one. Now new PC is assigned to PC, exactly the same thing happened to IO. Okay, then so far we have talked about interrupt mechanism has assumed basically have one simple assumption is that one interrupt happens at a time. That is basically what we have, the problem we are mentioning. We only have one OPC. One OPC, it means whenever we have something that is going to be interrupted in the middle of the interruption, it means the OPC will be getting overwritten. This is the problems. And this problem will be calling, is having a name, specific name for that. It will be called nested interrupt scenarios. For example, let's say, suppose we are in the middle of the service of a disk IO interrupt in supervisor mode. Then we have a timer interrupt or another service or another device interrupt comes in, or maybe the IO interrupt triggers when we are in the middle of the system call routine, such as the single OPC register. Then we have the problem is the OPC will be overwritten by another interrupt. It means whenever we're coming back from that interrupt, we cannot resume to our user program. You simply go to another interrupt, presume cycles, and nothing really get executed. Your program simply get aborted. So how we can handle this problem, how we can handle this nested interrupt is by designing a new mechanism, which is called, or having a new data structure, that is stack data structure. The stack will allow us to save multiple return addresses or other states in a last in, first out order. So every time a new interrupt comes in, we simply push the current context onto the stack. And each time an interrupt handler finishes, we simply pop the context to resume. But how we can implement this? So let's say we have a existing OPC register as a makeshift stack pointer. So in other words, rather than having just one fixed OPC storage, OPC register, we will treat OPC as a pointing to a location in memory. So on top of the stack where the return address can be stored. So therefore, we simply refer this OPC as, you have already heard this word, stack pointer, SP. So the SP will indicating where in memory the next value should be pushed or popped. By renaming this OPC to SP, we are repurposing that register. So this is no longer directly holding the return address. It's pointing to a stack that is holding multiple return address. So how we can do that? Basically, we have two steps. Step one, we design or designate OPC as our new stack pointer by basically renaming it and to be a stack pointer register. Then step two, we will adjust our interrupt routine by pushing the memory instead of storing in a single register. With this stack mechanism, so nested interrupt are no longer an issue. So each nested calls return address goes to the stack, preserving the ones below it. We are essentially extending our interrupt handler logic to be more capable of being interrupted itself. So this concept of stack is very critical, as it is not just for the nested interrupts, but generally for subroutine calls and returns in complex programs. So in a natural solution here. So think about what we have done in homework 3, that step-by-step slide I have for you. So that's a tiny piece of like block, which is tracking the recursion stack. That recursion stack is telling you which is the current running program, which is the function or program is calling that function. So that's basically the same idea what we have here. Simply, we have a way to track the current return address, or who is the next return address. Can we have multiple return addresses? Then what we have here, to implement this idea, we simply have restored this OPC to be SP, pointing to a memory slot that's holding the stack. So it will be increment SP if we have something get stored right there. If we're talking about increment SP, it means the direction of this stack operation will be what? SP is equal to SP plus 1. So then the direction will be what? Upwards or downwards? Upwards. Great. Great. So that's the only addition to the von Neumann machine. And that's the only change we are dealing with here. But now, to incorporate this idea to this interrupter cycles, we have to revise what our interrupter cycle in pseudocode based on what we have doing the modification. So OV, MP, PI will be exactly the same. Nothing really changed. Simply, we have a ban. We are going to abort those traps whenever we encounter one. Simply, they are invalid. They are errors. Then we come into the interrupt, IO interrupt. Simply, we are going to have the PC is recorded to the memory SP. That's it. That's the stack we're talking about, SP increments, and everything else will be resumed the same. And SVC equal to 1, exactly the same procedure. PC to record to the memory SP and SP plus 1. That's it. Nothing really fancy here. The only thing we are going to change is pseudocode is right here. And next thing we have to revisit is PSW. Now we have talked about SVC. SVC is going to add it as a part of PSW. PSW now is holding OV, MP, PI, IO, and SVC. That's it. That's a new addition. Then we come into something that is, we have covered IO and software interrupt. They are all great, but it is not necessarily cover all the scenarios. There are one more critical interrupt for the operating system, which is timer interrupt. So why do we want to timer interrupt? Have you ever considered this question? Anything? Nothing? You have ever thought about this? Yes? Mm-hmm.
I've heard of like things where using it goes forever until losing up 100,000.
AWS doing that? AWS is an awful service. Then it is. Okay, so what do we have here? Even our use case is having this mechanism for the timer interrupt. So why do we need a timer interrupt? So what if a program gets stuck in an infinity loop? For example, you are writing your homework 1. That is why I'm just saying, while you are writing your homework 1, you have implemented something went wrong and it goes to fetching some let's say invalid memory slots. It going to forever executing, basically infinity loop. And simply without timer, your program could potentially simply hog the CPU forever, holding that resources never being released. That is, your program is doing that. But OS would never get a chance to intervene or switch the task because unlike IO or traps, nothing external will break that loop. And to prevent this single, for example, your homework 1, you have got to write something went wrong. And the simple program from monopolizing the CPU, we use a hardware timer. So the concept is we have a special register that is called timer. And the OS is setting to a certain value. For example, time slide or quantum of time. So this timer counts down at each clock tick. So while the program is running. So if the program runs long enough, the timer simply reaches to 0 and the hardware will automatically trigger that timer interrupt. So let's denote that timer interrupt to be TI, to be here. And when the TI goes to 1, simply flag this TI to be 1. It signals the program timer sleds is up. So the CPU will then transfer this control to the OS timer interrupt handler. In fact, it is a safeguard. No matter what a program is doing, even if it's an endless loop, the timer interrupter will eventually fire and yank the CPU away from the programs into the OS. That is why once you have an infinity loop running on Eustace, you just simply abort your program and simply say, whether it's a segmentation fault or something else, that is the timer kicks in. Now we have on this slide simply provides you an overview about how timer fits in our system, in our CPU design. So we have a supervisor mode, which is incorporating everything. We have PC, TI, OV, and everything here. Interrupt cycle is only modified by the supervisor mode. Those registers can only be modified by the supervisor. User mode can only modify the accumulator register. And what we have addition to this, we have a TI flag and a timer. That's it. That's only addition to that. Then once we're talking about TI, then coming back to our PSW, this is the final stage we have for the PSW introduction. That is, we have in the OV, MP, PI, TI, IO, SVC, and mode. So at least for here, that's it for the PSW. So I won't stop right here. I don't want to rush through the lecturing so that it's getting too condensed in one place. Okay, so at least here, and thank you for coming.